And then following this section, there was a section on the respiratory cycle, and you saw a diagram that was very similar to our cardiac cycle diagram. I don't need you to know all the details in terms of amounts according to that diagram, for instance. This is the basic information that I need you to remember about the respiratory cycle right here on this review slide. The respiratory cycle is a single cycle of inhalation and exhalation, right? The amount of air that you move into and out of your lungs during a single respiratory cycle, that is called the tidal volume, the TV. And that should be approximately 500 milliliters in and out, with approximately 150 milliliters stuck in what's called the dead space. And dead space we discussed earlier, and we will also now look again at the dead space. Right. I wanted you to compare and contrast what's called the anatomical dead space and the physiological dead space volumes. The anatomical dead space is what we discussed on the first sheet here. This is the volume of air that is stuck in the air passageways during inhalation, where there is no gas exchange possible. Those are the conducting zones. And on average, that's about 150 milliliters of air. However, that's based on an average sized male. The actual anatomical dead space should be calculated for the individual based on their body size. But we'll just use 150 milliliters as our normal value, if you will, for anatomical dead space. Physiological dead space is even more variable. Particularly so for individuals that have cardiovascular issues. So this is the volume of any lung area where alveoli are not being perfused with blood. Right? And so this means that the perfusion for the individual is not normal. So typically we're going to see an increase in this physiological dead space area within the lungs for individuals that have any type of cardiovascular disorder that is decreasing their cardiac output. Right? So that could be congestive heart failure, for instance. If they're not adequately perfusing all the areas of their lungs, there's going to be some areas where the air is there, but there's no blood in order to allow for gas exchange to occur. And so those would be areas that we call the physiological dead space areas. And like I said, this is much harder to calculate for an individual. But we do talk about the general concept of this when we talk about perfusion and ventilation matching in our external-internal exchange lecture. And we talk about it briefly here in this lecture as well. Now, knowing how we calculate the respiratory cycle or determine the respiratory cycle based on the volume of air, and we know what the anatomical dead space is, we can calculate our total ventilation rate. Total ventilation rate is abbreviated as TVR. This would be the amount per unit time. So it's a flow rate for air. Right. We also think of this as our ventilation rate, if you will. Just refer to it basically as ventilation rate. We calculate it by multiplying the tidal volume, the amount that's taken in per breath, with your breathing rate, your breaths per minute. And we see what here in the units cancels out. We're left with the volume per minute. Very similar to cardiac output in terms of heart rate times stroke volume. And here I just do a quick calculation using the example that was given here. If we have tidal volume 500 milliliters per breath, and we count how many breaths an individual takes in a minute, let's say they take 12 breaths, we just multiply those two numbers together, and here we get 6,000 milliliters per minute, right? So 6 liters per minute. We can make a more accurate estimate of the ventilation rate called the alveolar ventilation rate, or AVR. Here, we're accounting for the dead space volume, just the anatomical dead space volume for the individual. So this will more accurately estimate the volume of air that's reaching the spaces where gas exchange is actually occurring. So let's assume that the individual is an average-sized male and they have a dead space volume 150. Then we just subtract that dead space from their tidal volume. So 500 milliliters minus 150. We'll use the 12 breaths per minute, and we're going to get a lower ventilation rate, having accounted now for that dead space volume at 4,200 milliliters per minute.